Hello everyone and welcome to this video where we will start talking about gases and the kinetic theory of gases. First of all, by now you know that matter is any substance that occupies a certain space and have a certain volume. You have the matter in either one of those three states, either solid, liquid, or gas. If it is solid, it have a fixed shape and a fixed volume, but if it is liquid, it will have a fixed volume, but it will not have a fixed shape. It will just take the shape of your container. Now, if you have a gas, it will move in all directions and it will have no fixed shape or fixed volume. Now, let's look at the kinetic theory of gases. First of all, you know that any chemical reaction, we need to assume how much gas, if we are working with a reaction that will produce gas or consume gas, we need to predict how much gas or how much pressure we should apply in these reactions. Now let's look at the kinetic theory of gases. Why we are interested in studying gases? This is because some reactions you need to apply certain pressure because one of your reactant is a gas, or you need to anticipate the volume of the produced gas because you don't need to have to accumulate a pressure of a gas due to the product of your reaction. One of the product is a gas. Now, the kinetic theory of gases, this kinetic theory explains or studies the ideal gas. The ideal gas in general is a gas where you have, in that case, the ideal gas in general, you have the gas molecules move rapidly and randomly, and the distance between the particles of gases is much greater than the diameter of your particles. This is why the volume of the molecules is almost negligible. So if you have molecules of gas, you will consider the volume of your molecules to be zero or negligible. You will just cancel it when you are looking at the equations. Now, there is no force for the ideal gas, there is no force that would attract any particles toward each other, and the collision, you will assume that it is completely elastic collision. This means any particles, when it hits another particle, it will not lose any energy. So no kinetic energy is lost during collision associated with the moving of the particles. Now, the temperature of the gas is related to the average kinetic energy of your molecules, and if you increase the kinetic energy, this means the temperature increases as well. Now, you have to remember that those conditions are only applicable for the ideal gas. But what if I don't have an ideal gas? Similar to that, any other gas we consider to be a real gas. Real gases, you have to remember that such as noble gases, such as helium, neon, there is an intermolecular force between those small particles which have a considerable effect on how gas behaves. So you have intermolecular forces between particles. Collision is not equivalent to zero. Actually, there will be a loss of kinetic energy due to the collision. So there is no elastic collision, and also the particle of gas not just interacting with each other. The molecules of gas have a certain volume that should be considered. Now, for any gas, it has this certain volume that it occupies, and we will measure the pressure of the gas using Pascal unit, and the temperature we will measure it using the Kelvin unit. Now, the relation between the gas volume and the pressure, what we call Boyle's law, at constant temperature, we will assume a constant temperature, the volume is inversely proportional to the pressure. This means if I increase the volume, I will decrease the pressure. Now, you could see here in this scheme, you could see that the particle of gas is far away from each other. When the piston is pulled out, this means I have here larger volume. So here I have large volume. This is why I have low pressure. In here, I decrease the volume. So this is when I push the piston down. This means I decrease the volume. This is why it means that the pressure increased. So if we just write, if we represent out in a graph the relation between the pressure and the volume, you find it that it is a curved line. Now, the relation between the volume and temperature, on the other hand, which is considered to be Charles' law, we will consider the relation between the volume and the temperature at constant pressure. In that case, we will hold the pressure as constant, and now you have the volume increasing, which will means the increasing of temperature as well. So you have a proportional relation between the volume and temperature. If we looked at this figure, you could see that the particles of gases, when at low temperature, they occupy a smaller volume than when I increase the temperature, they will start to move far apart from each other, creating a larger volume or occupying larger volume than at lower temperature. If we draw a graph between the volume and the temperature, we'll find it to be a straight line that passes through the point of origin. Now, the relation between the temperature and the pressure, on the other hand, we will name it Gay-Lusic law. This assume, on the other hand, the constant volume, and the relation here will be proportional between the pressure and the temperature. You have the relation as a straight line between the pressure and absolute temperature in that case. Now let's look at the three laws together. Now, the Boyle's law, we said the V is proportional to T, and Charles, we said V proportional to 1 over P. This means V is proportional to T over B, and if I replace the proportional with a constant, this means in that case V is equal to R T over B, where my R in that case will be the gas constant. So in general, we could say that VB is equal to RT. Now, there is a limitation in this ideal gas law. First, you have to remember most gases doesn't act as an ideal gas, but instead they act as a real gas. So there is an attraction between any molecules, that, like I said before, in the case of ideal gases, and also the volume of the molecule shouldn't be ignored, so it should be considered. If you have a molecule, you should consider the volume of those molecules. If you looked at high pressure and very low temperature, this is when we will find a very large deviation from the ideal gas law. Here, the molecules are so close together because you have a high pressure, you are pushing the molecules together. And on the other hand, at very low temperature, this means the volume of molecules is not negligible comparing to the volume of the container, because they actually, in that case, the volume of the container will just decrease so much due to the compressing of the gas. There is a considerable attraction forces between molecules because you have a lower temperature, so you're pushing the molecules together, and these molecules will start to interact together between each other. So you will have a considerable forces that will act between the molecules, such as van der Waals or dipole forces. Now, the attraction forces would pull the molecules together away from the wall of the container. So the idea is that if you have a container, now the attraction force between the molecules will push those molecules away from the wall of the container. This will create a pressure lower than the ideal gas. So the real gas will have a lower pressure than what is expected in case of ideal gas. Effective volume of the gas is even smaller than the ideal gas due to the attraction between the molecules that will decrease the volume that the gas should occupy. Now, what we mean by the term ideal gas? Again, if I have a question like that, how can I answer it? So we should say that ideal gas will have a volume that varies exactly in proportional to temperature and exactly inversely proportional to its pressure. In general, V is proportional to exactly T over P. So I have here is proportional and here is inversely proportional. This is what ideal gas is. Now, under what conditions do real gases differ from ideal gas? In that case, it will be at a very high pressure and very low temperature. This is when my real gas will deviate from the ideal gas because the molecules will be much closer from each other. This will create a considerable attraction force that will make my pressure and the volume less than the actual pressure and the volume considered or calculated for the ideal gases. So usually we put the three laws together and we name them the general gas equations. And general gas equation is a sum up of the three laws, which states that like Boyle's law, V is proportional to T, and in that case V is inversely proportional to 1 over P. And the last law, which is Avogadro's law, V proportional to N as well. So if we put those three together, we will get the general gas equation, which states that the BV is equal to nRT. This came from the V is actually proportional to NT over P, and we just should replace the proportionality by a constant which is R. So we have V is equal to R NT over P, and if we move the P to the other side, this means BV is equal to nRT. Now you know by now that B is a pressure, V is a volume, and N is the number of moles of your gas, and R is the gas constant, and T is a temperature. Now let's use the general gas law in solving some examples. In here, calculate the volume occupied by 0.5 mole of carbon dioxide at pressure of 150 kilopascal and temperature of 19 degrees centigrade. This means I have here in Pascal, in kilopascal, I have to convert it into Pascal by multiplying by 1000, and in here I have to find out the temperature in Kelvin. In that case, it will be equal to 19 plus 273. This means it is equal to 292. Now you could see that I need the volume. I have here the number of moles, which is N, and I have here the P, which is the pressure, and I have the temperature, which is in Kelvin. Now if I looked at the general gas law, it states that BV is equal to nRT. So if I substitute in that case, I need the V on one side, so it is V equal nRT over P. This means it is equal to, the N is equal 0.5 multiplied by the R, which is the 8.31, multiplied by the T, which is equal to 292, divided by 150,000. This is equal to 8.09 multiplied by 10 to the power minus 3 meter. So we can convert it into decimeter, cubic decimeter. In that case, we can multiply this by 1000. It is equal to 8.09 decimeter. Now let's look at another example. Calculate the volume occupied by 292 grams of methane. Now I have the mass. At a pressure of 250 kilopascal, I have the pressure, but I have to multiply it here by 1000 to convert it to Pascal, and at a temperature of 54 degrees centigrade, this means temperature in Kelvin would be equal to 54 plus 273, which is equal to 327 Kelvin. And I know that the molecular formula of methane is equal to 16. I need the number of moles. For the number of moles, it is equal to mass over molar mass, which is equal to, in that case, 272 divided by 16. This means I have 17 moles. Now, if I looked at the BV is equal to nRT, again, what I need to know is the V. This means V is equal to nRT divided by P. And I have the N, which is equal to 17. My R is equal to 8.31. And the T temperature is 327. Divided by, in that case, the P is 250,000. This means it is equal to 0.1848 meter, which I can convert it to decimeter, cubic decimeter in that case, by multiplying by 1000, so it is equal to 184.8 decimeter. when 0.08 grams of liquid X was vaporized at 100 degrees centigrade and 23 cubic centimeter of vapor was formed. So I have here in that case the temperature and the volume, and I have here the mass. The atmospheric pressure was 1.02 multiplied by 10 to the power 5 Pascal. Calculate the relative molecular mass of the liquid, knowing that R is equal to 8.31. So you have the mass, in that case, is equal to 0.08 grams. And your temperature, you should calculate it, in that case, it is 100 plus 273, this means it is 373. Now the volume, on the other hand, in here I have it in cubic centimeter, but we need to convert it into meters. This means I have, in that case, to multiply by 10 to the power minus 5. So if I have 23 multiplied by 10 to the power minus 5 to convert it into meter, this means I have 2.3 multiplied by 10 to the power minus 4 meter. Now I have the pressure in Pascal, so there is no problem with that. I have 0.02 multiplied by 10 to the power 5, and lastly I can just I have R, which is equal to 0.31 joule per Kelvin per mole. Now I can just apply the general gas law. I have BV equal nRT, and for that, in that case, I have the N. I need the N. This means the N is equal to BV over RT. So I have 1.02 multiplied by 10 to the power 5 multiplied by 2.3 multiplied by 10 to the power 4. This is the volume, and this is the pressure, and divided by 8.31, which is my gas constant, multiplied by the temperature 373. This is equal to 7.569 multiplied by 10 to the power minus 3 mole. Now I need the molar mass. So the molar mass, because I have here the value of, in that case, the now I need the molar mass. Now I have the volume of the gas. This means if I have the N and the M, I can get the molar mass. So the molar mass is equal to M, my mass, over N, which is my number of moles. So I have, in that case, 0.08 divided by 7.569 multiplied by 10 to the power minus 3, which is equal to 10.57. So my molar mass is 10.57. By that we came to the end of the first part, the gas law, the general gas law, and the kinetic theory of gases. Until next video, thank you and goodbye.